Okay, welcome to another installment. I love that word. Another installment of our notes on Unit 2 in IB Physics SL. This is thermal physics, and it has, as we've seen already, a review of some chemistry. In this video, we're going to talk about uh, a little bit more about heat exchange, or really we should say thermal energy exchange. And when we talk about it, we will finally start to see some equations we can attach to that physical situation. So we know already this fact. We know that substances exchange thermal energy when they're in contact, thermal contact. So what does that mean? Let's talk about this physical situation a little bit more. You have a frying pan and you heat it up. Maybe you've got something inside. You're cooking, you heat it up, and then you turn off the burner and you want to cool off that frying pan because it's just a little too hot. It's not very safe for your little sister nearby. So what do? You bring some water over and you dump the water out into the frying pan, and the water kind of fills the frying pan. Because the frying pan is at a really hot temperature and the water is at a really cold temperature, when they come into contact, they will start to exchange thermal energy, they will exchange heat, and specifically the thermal energy will go from the hot frying pan to the cold water. So what does this look like? Well, I don't know, let's do maybe some little squiggly arrows or something. Heat goes from the frying pan to the water temperature gets hotter, and the frying pan gets cooler. So we can attach some equations, some values here. I'm going to make up a number. I'm going to say, let's assume Q, how much thermal energy, how much heat does the frying pan exchange? I'm going to make up a number and say the frying pan gives away 10.0 joules of heat to the water. If the frying pan loses heat, then it's negative Q. The water, on the other hand, is gaining that 10 joules, which means the Q, the thermal energy, Q is thermal energy, the thermal energy of the water is positive 10 joules. Positive meaning energy is gained. And the negative means energy is lost. So thermal energy can be positive or negative depending on which is gaining and which is losing energy in the exchange. The hotter object always loses energy, and the colder object always gains energy. So what did we just see? Let's summarize. When thermal energy is absorbed by an object, right? When Q is positive, the temperature clearly rises. And when the thermal energy is lost by an object, right? When Q is negative, the temperature drops for the object. But here's an interesting question. Let's say we have 1 kilogram of water and we have 1 kilogram of gold. Gold is yellow and sparkly. We heat these substances, each of them, there's my flame, the fire, and we heat them such that the water absorbs exactly absorbs 1 joule of thermal energy, gold absorbs exactly the same amount, 1 joule of thermal energy. What do you think? If the mass is the same and the amount of absorbed energy is the same, should they have the same rise in temperature? Actually, the answer is no. You will be shocked, maybe. Shocked and, yes, just shocked. The water rises by so positive, by about 0.2 degrees Celsius. And the gold, on the other hand, rises by a whopping 7.7 degrees Celsius. The gold, as you see, is much more sensitive to added heat, and the water is much less, its temperature is much less sensitive to added heat, because it did not go up that high in temperature. So how do we compare how sensitive in temperature different substances are when heat is absorbed? We use something called specific heat capacity. Which has the variable C. So here's the official IB definition. Specific heat capacity is the amount of thermal energy that's needed to raise the temperature of 1 kilogram of some substance by 1 degree Celsius, which is also equal to a temperature change of 1 Kelvin. That's the definition. There's an equation as well for specific heat capacity. You're probably familiar with it. Specific heat equals Q, the thermal energy, over M times the mass, times the change in temperature. Or you may know the equation like this. Q equals MCAT, that test you take to get into med school. As you can see from the top equation, the units for specific heat capacity are joules, because joules are the units for Q. The unit of mass is kilogram. The unit of delta T can be either a degree Celsius or a Kelvin. A change of 1 Kelvin is no different from a change of 1 degree Celsius. We saw that in class today. And we can also rewrite this as a joule, kilogram to the negative 1, degree Celsius to the negative 1, like that. The specific heat is something that doesn't change for a particular substance in a particular state. C, little c, doesn't change. Here's what I mean. Liquid water has a specific heat which is always equal to about 4.2 joules, kilogram to the negative 1, Kelvin to the negative 1. Solid water, ice as we call it, in the normal world, has a specific heat, or specific heat capacity, of 2.0 joules times kilogram to the negative 1, Kelvin to the negative 1. This top number tells you it takes 4.2 joules to raise the temperature of 1 kilogram of liquid water by 1 Kelvin. The bottom value tells you how much heat, how much thermal energy does it take to raise the temperature of 1 kilogram by 1 Kelvin. It takes 2 joules of thermal energy to raise 1 kilogram of solid water by a temperature change of 1 Kelvin. So let's do an example, a couple examples. I have some mystery substance X, and its specific heat is 1 joule per kilogram per Kelvin. And I have another substance Y, whose specific heat is 1,000 joules per kilogram per Kelvin. Let's look at two extremes. How much heat does it take to raise 1 kilogram of substance X by 1 Kelvin? How much thermal energy is needed? The answer would be just 1 joule. That's not very much thermal energy. How much energy, thermal energy, would you have to add to make 1 kilogram of substance Y increase by 1 Kelvin? You would have to add 1,000 joules. Substance Y requires way more heat to get just a single Kelvin of temperature increase. Substance Y is less temperature sensitive to added heat, and substance X is more temperature sensitive. So let's write something down to capture that. Let's see. The higher the value of specific heat, the less temperature sensitive the substance is to added heat. Oh, added thermal energy. So substance C had a small specific heat, just 1, and with just 1 joule, it jumps up a Kelvin. That's pretty sensitive. Substance Y had a huge specific heat, and it means that you have to put in so much energy to even get 1 single Kelvin. So the higher the value of C, the less temperature sensitive the substance is to added thermal energy.